Hey everybody, Morgan here. So we're starting a new chapter in AP on acids and bases. It's a new outline, page number 1. We're going to start off with a brief review of the concept of electrolytes. Now an electrolyte is something that dissociates in water and conducts an electric current. Now, we could basically just be saying, something that's ionic, because that was also how we described ionic substances. But it does hold for polar covalent also. Now, strong electrolytes. A good example of a strong electrolyte would be something like NaCl. And it fully dissociates and is a good conductor. Now, a weak electrolyte, a good example would be something like acetic acid, which partially dissociates and is a poor conductor, but it does conduct. It conducts. Now, ionic and strongly polar covalent substances are strong electrolytes. Weakly bonded, not a big difference in electronegativities would represent the weak electrolytes. Now, non-electrolytes are purely covalent things like methanol, CH3OH, no dissociation, no conduction. All right. Now, the reason we bring this up is that acids and bases are electrolytes. Now, maybe you remember a couple simple things about acids and bases. We say acids are sour, bases are bitter. Do not taste the chemicals, people. But you know this from like biting into a lemon or maybe even the taste of soap. Okay, if it's ever gotten in your mouth when you were washing your face. Okay? Acids turn litmus red, and bases turn litmus blue. Okay? There are other things we could add to this list. We'll get back to that as we go throughout the chapter here. Okay. Now, for some actual definitions, for some models, okay, we're going to start with Zavant Arrhenius. Okay, he's the guy that basically talked about ions in the first place and how things could ionize. And according to his model, acids are H plus donors and bases are OH minus donors. Okay, HCl would be an acid and AOH would be a base. When we have things that start off with H and then the anion, it's typically an acid. Bases are typically ending in OH. But that doesn't cover all of them. And for that reason, we had to expand and come up with some other theories. Now, this one was done about 1880, give or take. I couldn't give you an exact year. But it was before we knew about the existence of protons and electrons. So when both Bronsted and Lowry, independently of each other, modified the theory, mostly because of the compound ammonia, the acid definition changed to being a proton donor. That's the same thing. It's just a different name for an H+. Okay? But bases became proton acceptors. So NH3 can accept an H plus and become NH4 plus. Okay? Now still, this reaction is a nice illustration for Bronsted-Lowry theory. It was about 1900, 1910, somewhere in that range. Now in the 1930s up at Berkeley, Lewis and primarily his graduate student, who was Glenn Seaborg, came up with a completely different model. Acids are electron pair acceptors, and bases would be electron pair donors. And this was primarily because of BCl3. Now boron, chlorine, 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 no lone pair, less than an octet. Take ammonia, which has got that lone pair. That lone pair bonds right in there, and what we end up getting is B bonded to N, H, 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 Cl, Cl, Cl. Okay? So those are our three theories behind acids and bases. It goes deeper, actually, when you get into advanced inorganic chemistry, but that's plenty enough for what we're doing. Okay, let's look at conjugate acid-base pairs on page 2. An acid, something like HA. Now, A just meaning the anion, generic. Plus water, we always react these with water because they're electrolytes. Gives us H3O plus and A minus. Now, HA is our acid, which means A minus will be the conjugate base. Acids react with bases, so H2O would be acting as a base, and H3O plus is its conjugate acid. What's the difference between an acid and its conjugate base? One hydrogen, really. That is the only difference. So this could be something like HCl plus H2O, giving us H3O plus and Cl minus. This would be a conjugate pair, and that would be a conjugate pair. Now, for bases, we could just say generically A minus. Doesn't have to have a negative charge, though. H2O gives us OH minus and HA. This is a conjugate pair. This is a conjugate pair. This is the base, making this the conjugate acid. This would be an acid, making OH minus the conjugate base. And as you can see here, water can react as both an acid and a base. Okay, we call that amphiprotic. Good example of this is ammonia Nh3 reacting with water gives us NH4 plus and OH minus. Now, let's watch the charges carefully. When you gain a hydrogen, you go up in positives. So this was a negative, and it went up to a 0. That's fine. This was a 0, so it went up to a positive 1. Okay, why don't you actually take a second and see if you can write these 10 equations for them reacting with water, and then tune back in. Now, hopefully, what you got was H2O, gives you H3O plus and NO3 minus. Did I mention you need to know your polyatomic ions? H2O gives us H3O plus and the acetate ion. Plus H2O gives us H3O plus and Cn minus plus H2O gives H3O plus and OCl minus. Now those are all acids. These do not start off with an H, do they? These are bases. So they add a hydrogen. We get CH3 and H3 with a positive. And OH minus plus H2O. We get HF plus OH minus plus H2O gives us NH4 plus and OH minus plus H2O. Actually, we have this one up at the top of the page. H3O plus and Cl minus plus H2O gives us H3O plus and Br minus and then plus plus H2O gives us H3O plus and I minus. Okay? And you could go through and do the conjugate pairs if you like. Wouldn't be a bad exercise. Okay. So now, we should talk a little bit about how equilibrium is going to impact this chapter. We have Ka, which is an equilibrium constant for the dissociation of an acid, which would be like H3O plus times A minus divided by HA. And we can have a Kb, which would be OH minus times HA divided by A minus. Now, these are related to each other based upon this reaction. The autoionization of water. H2O liquid breaks down into H3O plus aqueous and OH minus aqueous. And Kw is the equilibrium constant for that, which equals the concentration of H3O plus times the concentration of OH minus. And if you look up here, you'll see that that equals Ka times Kb. So as acid strength goes up, base strength goes down for the conjugate. Okay? They're inversely proportional to each other. This is the 1K where we actually ask you to know the number, 1.00 times 10 to the negative 14 at 25 degrees Celsius. Okay. Now, I'm going to round off this page just filling in some random things about acids and bases that are going to pop up, and I just thought it was a good place to just stick all of it. The concept of indicators. Indicators are chemical dyes that can exist in at least 2 different forms based on pH. So they change their chemical structure, lose a hydrogen, gain a hydrogen, they change color. We used phenolphthalein a lot back in honors, so you're probably remembering them. Okay. Now, this table is actually a great table. You can answer a lot of questions with this. Okay. For a strong acid, for a weak acid. Let's compare some of their just typical properties. Okay. Now, there are a lot of different ones that we could choose to fill in here. I like to start off with Ka. Ka for a strong acid is big, and it's small for a weak acid. All right? The next one that we're going to put in here is going to be the equilibrium position. The equilibrium position is on the product side for a strong acid, and it's on the reactant side for a weak acid. Okay? Now the concentration of H plus for a weak acid, for a strong acid, the H plus is equal to the HA because it fully dissociates. But for a weak acid, the H plus is much, much less than the concentration of the original acid because it only dissociates partially. Now we also have the conjugate base. The conjugate base of a strong acid is weak, and the conjugate base of a weak acid is strong. Okay. Now, just in case you've forgotten, it wouldn't be a bad idea just to remind you that the 6 strong acids are HCl, HBr, HI, H2SO4, HClO4, and HNO3. Okay, how about polyprotic acids? Polyprotic acids are capable ionizing more than one hydrogen. So, H2SO4 can react with water, and stepwise, the first step is that it gives off H3O plus and then HSO4 minus. Then the HSO4 minus can go and ionize itself to give H3O plus and SO4 2 minus. Kind of important to note that the H2SO4 does not give off both hydrogens simultaneously. It has to go through these two steps. Now, HSO4 minus is another one of these amphoteric or amphiprotic species. It can be both an acid or a base. So can water. So these are capable of either gaining protons or losing protons. They're capable of being an acid or of being a base. Okay, that's the first 3 pages of this one. And when we tune back in, make sure you have your calculator with you. This is Morgan, signing off.